So, we got started with sampling, and the idea of sampling, we started with impulse train sampling, that is a theoretical construct. Therefore, given xc of t, we multiply by p of t, which is an impulse train, and this gives us the sampled signal. And then we were looking at the continuous time Fourier transform of the impulse train sampled signal. Therefore, this is between minus infinity to plus infinity xs of t e to the minus j omega t dt, and p of t of course is the impulse train. So, this is k going from minus infinity to plus infinity, delta of t minus k cap t is the impulse train, cap t is the sampling period, 1 over t is called as fs, and this is the sampling frequency. And this we saw was nothing but k going from minus infinity to plus infinity xc of k cap t e to the minus j k omega by fs. So, this was the expression that was derived towards the end of the last lecture. Remember, our goal is to relate the continuous time Fourier transform of xc of t. Xc of t has continuous time Fourier transform xc of cap omega, and the other sequence that we are interested in is x of n, which has discrete time Fourier transform x of e to the j omega, and x of n is nothing but xc of n cap t. These are the values of the signal at the sampling instance, and our ultimate goal is to relate xc of omega and x of e to the j omega. So, we have come this far, but as you can see from this expression, on the right hand side you have xc of kt. So, we do not have anything that relates or that brings in xc of omega. So, for this we look at exactly the same spectrum, but from a slightly different viewpoint, and the viewpoint we are going to look at is this. So, we have xs of t, and this as before is xc of t times p of t, which is the impulse train, and we also know that if you multiply in the time domain, you convolve in the frequency domain. Therefore, from the multiplication in the time domain relating to convolution in the frequency domain, the expression now becomes xc of omega convolved with p of omega. So, xc of omega is the Fourier transform of xc of t, and p of cap omega is the Fourier transform of the impulse train. And if you recall, the Fourier transform of an impulse train is also an impulse train. The main difference is the spacing. If the spacing is t in the time domain, the spacing will be inversely proportional in the frequency domain. Therefore, the Fourier transform of this is 2 pi by t, cap t, where cap t is a sampling interval, k going from minus infinity to plus infinity, delta, it is again going to be an impulse train, but it is going to be spaced omega s apart in the frequency domain, where omega s is nothing but 2 pi by cap t. So, this is all from what you have learnt in the previous course, and hence excess of omega is now 1 over 2 pi xc of omega convolved with 2 pi by cap t, k going from minus infinity to plus infinity, delta cap omega minus k times omega s. All I have done is I have just replaced the corresponding expressions for xc of omega and p of omega. So, the 2 pi cancels. So, this becomes 1 over t, and then when you convolve something with an impulse train, it periodically replicates whatever you are convolving with. Therefore, this becomes k going from minus infinity to plus infinity xc of omega minus k omega s. So, this is the formula we will focus on for now, draw some inferences before moving on to connecting xc of omega and x of e to the j omega. Therefore, what this tells you is, this tells you that the impulse train sampled signal spectrum is a periodic repetition of the original signal spectrum. The original signal is xc of t, its spectrum is xc of cap omega, and now this is getting periodically repeated, and the periodicity in the frequency domain is omega s. So, periodic repetition is one thing. The other important thing to note is, not only is there periodic repetition, but there is also amplitude scaling, and this amplitude scaling is 1 over t, and hence you have amplitude scaling, and the scale factor is 1 over t. The other thing you have is periodic repetition, and the period of course is omega suffix s, where omega suffix s is 2 pi by cap t, and remember this can also be written as 2 pi times fs, because 1 over t after all is fs, and fs has units of hertz. So, again this all recap, this all going over what you have learnt in sampling earlier, and the picture that is normally associated with this is along these lines. So, you have xc of omega, and this is cap omega, and you have function something like this, and this is between minus omega c to plus omega c. So, this is the Fourier transform of the given xc of t, and then what you have is xs of omega, which is the periodic repetition of xc of omega, the periodic repetition being omega s. So, I am just showing a couple of copies, the fundamental and the copy to the left and copy to the right. So, this is omega c, this is minus omega c. The other important thing that you have to also keep in mind is the scale factor of 1 over t, and hence if you now have another sampling frequency, and suppose this sampling frequency is omega s1, and omega s1, suppose if it is larger than omega s, then the periodic repetition will occur later, So, this will be minus omega S1 and this of course will be 1 over T1. So, the amplitude scale factor goes up, the repetitions occur later. Again, these are not to scale, I have shown them by the same height, but what is really meant is the heights are also different. And just to complete the picture for one more case. So, this is omega S1 greater than omega S, and immediately you can also guess that if you now have a sampling frequency that is smaller, say omega S2, then the repetitions will occur sooner, and this will be scaled by 1 over T2. So, all these axes are omega, which is in radians per second. So, you have this signal, its sampled version, periodic repetition will be there, amplitude scale factor will be there, and the two plots below show the behavior for two different sampling frequencies, one that is larger than the first, the other that is smaller. And hence, immediately this brings about this picture. So, the repetitions will occur earlier or later depending upon whether the sampling frequency is lower or higher, and immediately you can see that if the sampling frequency is just about what is considered minimum, the repetitions will just abut each other. So, this is omega c, this is minus omega c. So, this is when the sampling frequency is what is called critical sampling frequency, that is they just touch each other, and the other case of course is undersampling. So, you have minus omega c to plus omega c, you have not sampled it enough, so that the repetitions occur so much sooner that they overlap, and this is what is called undersampling. Again, in these last two plots I have not shown the corresponding scale factor. Scale factor is implied. Here I am focusing on the overlap part. So, from this picture you see that this point would be omega s minus omega c, and you want this point to be at best equal to omega c or greater, only then will this repetition occur later, all right. Therefore, if you do not want overlap, then it is easy to see that you need omega s minus omega c to be greater than or equal to omega c. So, this implies that omega s must be greater than or equal to 2 omega c. And the other thing that is implied from the picture that we have drawn is clearly we have assumed the signal to be band limited. That is why this frequency response is between minus omega c and plus omega c, and there are no other components beyond this frequency range. So, assuming you have a band limited signal, and as I had mentioned earlier, this signal is low pass. So, what we are actually discussing is the low pass sampling theorem. you should be aware that there is also a corresponding band pass sampling theorem, which you are not going to look at. So, for the low pass case, signal is assumed to be band limited, and in such cases, if you do not want overlap, this is what has to be satisfied. And yes, question.
So why do we care about low pass band limited, even if it is a band limited at around some higher frequency? Even then we get repetition similar.
Yes. So what will happen when the signal is band pass? There also, as you rightly say, there will be repetitions, and then you can come up with a version of sampling theorem such that the sampling frequency required is not twice the highest frequency. That is the point. The point is, here what you are inferring is, you are inferring that for distortion to not happen, you need to sample at least at twice the highest frequency. If the signal were band pass, if you treat it as a low pass signal with the highest frequency being whatever the frequency is there in the spectrum, then you would end up sampling it at a far higher frequency than needed. Whereas, if you look at the band pass sampling theorem, you will infer that you do not need to sample it at twice the highest frequency, but something much lower. That is the inference that will be drawn. And this critical sampling frequency is called the Nyquist frequency. Therefore, this is critical sampling, and when you satisfy the theorem such that it just about these two repetitions abut each other but do not overlap, that particular sampling frequency is called the Nyquist sampling rate. And then this also you must have heard. So, these two overlap, and it should be clear that whenever you have something that is periodic, then you need to consider the information only in the range 0 to the period or between minus half the period to plus half the period. Anything outside this is the same, and hence since this is periodic with period omega s, either you need to consider the information in the interval 0 to omega s or between minus omega s by 2 to plus omega s by 2, because everything else outside this is the same, you do not get any new information. And hence, if omega s were the sampling interval, all you need to do is you need to consider the information between minus omega s by 2 to plus omega s by 2, that is all, and that is this dashed line. And when these two things overlap, you produce distortion, and this is what is called as aliasing, and hence the spectrum that you have is really this. So, this is the aliased spectrum. You cause distortion, and this is the distortion that is caused is called aliasing. And just to focus on what aliasing is, I am just drawing the positive part of the spectrum. Remember, this is omega s by 2, and only the information between minus omega s by 2 to plus omega s by 2 needs to be considered. And because of this, what is happening here is this portion folds over and appear as a low frequency. So, this is actually a higher frequency component in the signal originally. Because you undersampled, it appears as a lower frequency component in the undersampled signal. So, a high frequency component masquerading as a low frequency one is called aliasing, all right. And we will see a simple sinusoidal example where this is brought out. So, this is for the general case where I have assumed the signal spectrum to be like this and showing how a high frequency component folds over and acts like a low frequency one. And this, because you can think of this as being folded over and appearing in this also is called as the folding frequency. Another name that you will find in the literature is this omega s by 2 is also called as the folding frequency. So, this can easily be illustrated, this aliasing, which is really a higher frequency component appearing as if it is a lower frequency component because of undersampling, easily can be seen when you consider a sinusoid. So, let us consider a pure infinite duration sinusoid. Therefore, its frequency is transform is 2 impulses. So, I am assuming that f naught is 8 kilohertz. So, this is the frequency of the sinusoid. If I did not want aliasing, I need to sample at least at twice the highest frequency. Therefore, I need to sample it at 16 kilohertz or beyond if I did not want aliasing. Therefore, this is minus 8 and plus 8. So, this is f and this is now in kilohertz. So, now in this example I am showing the frequency axis in terms of hertz, which is nothing but omega by 2 pi for ease of calculation and reference. So, this is my underlying sinusoid. Now, what I am going to do is I am going to sample it at 10 kilohertz, which means everything in the spectrum will be periodic and the periodicity will be Fs. In the omega domain it will be periodic with omega s, in the Fs domain it will be periodic in Fs. Therefore, everything will repeat after 10 kilohertz. Therefore, what will happen is, if I now look at periodic repetition, minus 8 will occur at minus 8 plus 10, right. Therefore, minus 8 will now occur at 2 because minus 8 plus 10 is 2. Then 8 also will repeat later with a periodicity of 10 kilohertz. Therefore, 8 plus 10 is 18 and hence let me draw this with a different color. So, I will have 18 here. So, this is 2 repetitions on the right. So, things will also will repeat on the left. Therefore, 8 will appear at 8 minus 10. You saw 8 plus 10 here, 8 minus 10, 8 minus 10 will be minus 2 and minus 8 will also occur at minus 18. But also note that 2 will again repeat with a period of 10. Therefore, 2 plus 10 is 12, right. Therefore, so these are some of the repetitions here. Remember, what will happen at 0 will also happen at 10. Therefore, so this is 10 kilohertz. So, what will happen at 0 will also happen at 10. Therefore, you have this picture. And remember, whenever the frequency, sampling frequency Fs is Fs, you need to worry about the spectrum only between minus Fs by 2 to plus Fs by 2. Therefore, you need to only worry about the spectrum between minus 5 and plus 5, this is clearly not to scale, and whatever is happening around 0 will happen at multiples of 10 and minus 10. Therefore, now you have, when you concentrate between minus 5 kilohertz and plus 5 kilohertz, the original signal which was 8 kilohertz, because you are now undersampled, has now become 2 kilohertz signal. And what is happening around 0 is happening around 10. Therefore, around 0 you have plus 2 and minus 2. Similarly, around 10 you have 8 and 12. So, these are the other copies. And similarly, what is happening around 10 will happen around 20, and hence you will have 18 and 22. So, these are the further copies that are present, and hence you will have something like this. You will have minus 8 and minus 12, which is centered around minus 10, and similarly you will have minus 18 and minus 22. Therefore, a 2 kilohertz signal is now what appears in the spectrum, and this is a result of a 8 kilohertz signal being sampled at 10, which is inadequate, and hence the underlying spectrum corresponds to the spectrum of a 2 kilohertz signal, and hence a high frequency signal, namely 8 kilohertz, masquerading as a low frequency signal, namely 2 kilohertz, happens because of undersampling, sampling it at 10 kilohertz rather than the required minimum of 16 or beyond. So, this all the spectrum is. So, when you have a given underlying spectrum xc of omega, if you want to sample it at omega s or fs, all you need to do is you need to repeat that spectrum with a periodicity of omega s or fs equivalent to fs, and then focus on the interval between minus fs by 2 to plus fs by 2. That is all. And here is an example of aliasing. 8 kilohertz behaves as if it were a 2 kilohertz signal. The other thing to remember in this context is all practical signals are time limited. If a signal is time limited, what can you say about in the frequency domain? It will be band unlimited. Therefore, no time limited signal can be band limited, no band limited signal can be time limited, all right. Now, the implication of this is that since all practical signals are time limited, their frequency content in the Fourier representation will be of infinite duration, and hence you cannot sample them without causing aliasing, no matter what sampling frequency you use, because it is a band unlimited signal, you will always cause aliasing. One way to avoid aliasing is to use what is called an anti-aliasing filter. So, this what it does is it band limits the input signal. Once you have band limited this input signal, and if you now sample it, you will not cause aliasing. But if you look at this, because you have put this band limiting or aliasing filter at the front end, you are now going to lose some high frequency component, because you have band limited the signal before sampling. So, you have lost high frequency component. So, this is on one side. Now, you have to compare this with a signal. If you do not do this band limiting filter, if you do not introduce this and band limit the signal, if you sample, you are going to cause aliasing, because the signal is band unlimited to begin with. So, no matter what you do, you are going to distort the given signal. The question is, which is better? And the answer to this is this anti-aliasing filter at the front end is better, because in that case you only lose the high frequency component, whereas if you cause aliasing, not only are you going to lose the high frequency information beyond fs by 2, but that high frequency information is going to come back as a lower frequency component in the signal and cause distortion. And in practice, it has been found that this aliasing is perceptually very annoying, and hence all practical ADCs have a band limiting filter at the front end. So any ADC chip that you use will always have a front end anti-aliasing filter, and it has been found that this is less objectionable than aliasing occurring, because the high frequency component folds back and appears as a low frequency component. Fortunately, all practical signals have a spectrum that falls off with increasing frequency, and hence if you put this band limiting filter and remove beyond a certain point, the information lost will not be too much of an issue. Perceptually, it may not matter much. You choose the band limiting filter high enough so that all the relevant information is captured. For example, in telephony, in the first days of digital telephony, your voice signal was band limited to, do you know what the sampling frequency was, and hence what the, no, I am talking about early days of digital telephony. So what you are talking about 44.1 is what you use. It's one of the standards for music and other things, but telephony for voice, do you know what the numbers were, what the sampling frequency was? Not clear. No, this is too high. 32, no. So 8 kilohertz was the sampling frequency, and so in the sampling frequency was 8 kilohertz, and the front end filter was actually between 300 hertz to 3400 hertz. So this was the front end filter that was used, and then they were using 8 bits per sample, and this gave rise to 64 kilobits per second telephony rate, sampling rate. Again, 8 bits per sample is actually not adequate. You really need something like 12 bits, 12 or 13 bits, but they got around using 8 bits and still not sounding too bad, because they used what is called A-law and mu-law compression, all right, non-uniform quantization. That is, lower amplitude signals were quantized finer and higher amplitude signals were quantized coarser. Therefore, the 12 bits per second, which was what was needed if you used uniform quantization, that was overcome using just 8 bits by nonlinear quantization. And mu-law and A-law are the compression standards used in the US, and the other one is in Europe. Therefore, you just needed 8 bits per sample, and this gave 64 kilobits per second, and the anti-aliasing filter was 300 to 3.4 kilohertz. And this is the reason why you will have trouble listening or distinguishing between S and F, because the distinguishing features of these sounds lay mainly in the higher frequency part of the spectrum. Because of this anti-aliasing filter that got knocked off, that is why people will say S as in Sam, F as in father, right? When you try to say some letters as abbreviations, you will have trouble at the other end unless you clarify what it is, and that is why S as in Sam, F as in father is needed, because those sounds cannot be distinguished clearly at the other end, and that is because of this anti-aliasing filter that is cutting out high frequency components. Of course, now what we do is we do not use just plain sampling, we use speech coding. You sample it at a certain rate, we take 30 milliseconds of speech, sample it, and then use a source filter model and then transmit those parameters. So, the advantage is you get higher quality speech or you get a lower bit rate speech, but the price paid is more processing power. All this involves DSP processing. Anyway, coming back to sampling. So, anti-aliasing filter is an integral part of all ADCs. That is because you want to avoid distortion due to aliasing. And as I had mentioned, all practical signals, the spectrum decays fast enough so that you can put a reasonable band limiting filter and still not perceptually feel the difference between the filtered and the unfiltered signal, because the energy is so little beyond a certain frequency. Putting this band limiting filter is not a big deal. Now, let us come back. So, this was a digression for aliasing and what it does and how to mitigate the effects of this aliasing by putting this anti-aliasing filter. Now, let us come back to the problem at hand. Remember, our goal is to connect samples of this signal. So, this is k and this is x of n times delta of n minus k. So, this is your discrete time sequence, right. So, this is 0, 1, 2, 3 and so on, and this in turn really becomes x of k delta of n minus k because of the shifting property. And what we really want is we are trying to relate the DTFT of this sequence and the spectrum of the impulse train sampled signal. So, this is xs of t, this of course is xc of t, and the impulse train is the impulse train corresponding to xs of t. Now, we want to relate these two, that is we have x of e to the j omega. So, this is nothing but n going from minus infinity to plus infinity, x of n e to the minus j omega n, and this is nothing but n going from minus infinity to plus infinity. X of n is nothing but xc of n cap t, because these are just those sample values, e to the minus j omega n. So, this is one part of the problem. The other thing that we have just now derived is this xs of omega, and xs of omega we showed that this was nothing but n going from minus infinity to plus infinity, xc of nt e to the minus j n omega by fs. This was what we derived first, right. And what we had derived using this approach was to show the periodic repetition, the amplitude scaling by 1 over t, and then effects of aliasing. We will come back to this. This periodic repetition picture is very important. So, that periodic repetition picture was not present in this expression. But if you look at these two, you can now start to see the connection here. Let us take xs of omega. This is actually, this is omega s periodic. We got the picture about the periodicity of xs by the second approach. We know that this is omega s periodic. Now, let us consider y s of omega, and y s of omega is x s of Fs omega. So, what we are doing is we are forming a new function Ys of omega, which is a scaled version of Xs of omega. That is what we are doing here. And typically Fs is greater than 1. Therefore, one interpretation of this is Ys of omega is a compressed version of Xs of omega, right, because x of 2t is a compressed version by a factor of 2 of x of t, and hence to start to understand this, since typically Fs is greater than 1, you can think of Ys of omega as Xs of omega Fs. So, this is compression by a factor of Fs, that is what is happening here, all right. What about Ys of 2 pi? Ys of 2 pi is Xs of wherever omega is, you replace omega by 2 pi, therefore, this becomes 2 pi Fs, and this is nothing but Xs of omega s. Therefore, what can you say about the periodicity of Ys of omega? Ys of omega is 2 pi periodic. So, Ys of omega is 2 pi periodic. Now, what we will do is we will replace omega by little omega, that is in Ys of omega, which is 2 pi periodic, we will relabel the independent axis omega, cap omega by little omega, right, and write, remember now we have relabeled the independent axis from cap omega to little omega, and then write Ys of omega as x of e to the j omega. So, basically what is happening is, let us go back to this picture. Let us go back to this. So, Xs of omega is the impulse train sampled signal spectrum. It is periodic with period omega s, that is one thing. Of course, the other thing is the amplitude scale factor. So, all you need to do to relate this to the underlying sequences DTFT is scale the frequency axis by Fs, right, that is all. And why does that make sense? That makes sense because this is 2 pi Fs. If you now scale this by Fs, this point will now get mapped to 2 pi, and the DTFT is nothing but 2 pi periodic, that is all, as simple as that. And hence, to get x of e to the j omega, all you need to do is you need to take Xs of omega and then replace omega by omega Fs. Go back here, take this cap omega and replace cap omega by little omega times Fs, right. So, now take omega and then replace omega by little omega times Fs. If you did that, this Fs will get cancelled. So, minus j n times omega by Fs will become minus j omega n, which is exactly this, and Xc of nt is nothing but x of n, that is all, as simple as that, So, basically you are taking the impulse train sample signal which is omega s periodic and compressing the frequency axis by cap fs. So, that the omega s periodic function becomes 2 pi periodic, which is what the DTFT is. So, now what we will do is, we will start off with xc of t, then we know what its Fourier transform is, which is xc of omega. Then what we will do is we will form xs of omega. So, two things will happen when you go from xc of omega to xs of omega. First thing is periodic repetition with period omega s. The second thing is amplitude scaling. Then what we will do is we will take xs of omega and then replace omega by little omega times fs, and then we will see that this will give us x of e to the j omega. And we will do this by taking specific examples for which we know the CTFT and the corresponding sequences DTFT also will be known. What we will do is we will start off from the CTFT and derive the DTFT going through these steps for well known sequence functions, and then we will see that we will get back the same expression that was derived when we encountered the sequences DTFT. So, now you will be able to see the connection much closer.